Thank you very much. And yeah, so first I want to mention that, so what I'm going to talk about today, it's all joint work with Hao Shen, who's sitting over there, who's currently postdoc in Princeton and did his PhD in Princeton. So what I want to talk about today, it's essentially a new take on an old problem. And so the model, well, so let me first explain to you what's the sort of classical, the static Sine-Gordon model, if you want the quantum Sine-Gordon theory. Well, it's basically a field theory that's associated formally to the Gibbs measure, if you want, 1 over 1/2 integral gradient u square. I'm going to call my fields u instead of phi, and because I'm going to use phi for something else. So phi is going to be the free field, basically. So e to the minus integral gradient u square plus cosine beta u dx. And this should be thought of as, if you want, a density with respect to Lebesgue measure, which doesn't exist. Okay, so here there's sort of du. That's the Lebesgue measure, which doesn't exist. And u, you should think of it as being a field in 2 dimensions. And I'm going to put everything into finite boxes. Okay, so u should be thought of as a function from the 2-dimensional torus into R. Okay, and this is sort of Lebesgue measure on the space of functions from the 2-dimensional torus into R. And now, of course, you know, the way you would want to interpret this is to say that it should be, you know, this thing should be a Gaussian measure, and it's basically the free field. So you really want to interpret this as e to the minus 1/2 integral cosine beta u dx times Gaussian free field of du, if you want. Okay, and there's some normalization constant here. And the interesting thing about this model is that it's sort of a nice toy model for renormalization techniques, because the parameter beta here, as you're going to see in a moment, in some sense plays a similar role to what the dimension tends to play in other kind of field theories, in the sense that as you vary beta, the scaling properties of different objects actually change, and they depend on the value of beta. And then there are, you know, so if beta is too high, then the theory is not renormalizable at small scales, and if it's low, then it's renormalizable at small scales. So it's sort of like the dimension in usual theories, right, where they are badly behaved at small scales in high dimensions, and they are well behaved in low dimensions. Okay? So it's a nice toy model for that. But actually, it also arises from sort of more realistic models. So actually, if you look at the partition function for the grand canonical ensemble for the Coulomb gas, but for a neutral Coulomb gas, okay, so not the one that Sylvia talked about yesterday, where all the particles had the same charge, but a gas which is globally neutral. Okay, so you have the same number of positive charges and of negative charges, so they tend to bind into dipoles. And then that normalization constant is basically the partition function for the grand canonical ensemble. And constant in front of here would be something like a chemical potential, and beta would really be the inverse temperature. Actually, beta square would be the inverse temperature, but I still call it beta because I don't want to have square roots all over the place. Now, there's a natural dynamic, right? So you could view this as some sort of measure on a space of distributions. And of course, as usual, there's the problem of, you know, what does this actually mean? So you're going to see that if beta is too large, well, then in some sense, for certain values of beta, you can still make sense of this measure, but you cannot make sense of it in the way it's written here, in the sense that it doesn't actually have a density with respect to the free field. And this quantity here actually blows up in a way. But now there's a natural dynamical model which is associated to this, In the same sense that, in finite dimensions, if you have a measure e to the minus v of x dx, and x is in Rn, then there's a natural Langevin equation associated to it, which is just a gradient flow with white noise. Okay, and that's a sort of natural Langevin equation that has e to the minus v as invariant measure. So if you do this in the case of this model, what you end up with is this equation here. So dtu equal to 1/2 Laplacian u plus sine beta u plus xi, where xi here is space-time white noise. Okay, so if you want, it's Gaussian-centered noise, which is delta correlated both in space and in time. Okay, and formally, this is some sort of gradient dynamic that's associated to this model. And so if you can make sense of this dynamic here, then, well, that should be a Markov process whose invariant measure is this measure up here. Okay? And so what I'm going to talk about today is actually, the problem of making sense of this dynamic here. Now, actually, the dynamic itself was introduced also in the literature, in the physics literature, not so much. I mean, the time here, it's not, I don't think it has any, I don't know if it has any interpretation in terms of the Coulomb gas picture. But there is actually, the same model has been introduced also as a model for surface fluctuations for a crystal. Okay, and then this here sort of reflects the periodic structure of the layers of the crystal. And if you want, this is like the Edwards-Wilkinson model in this case, where you still have the effect of the layers of the crystals that appear. Okay, so the usual Edwards-Wilkinson model would be just this. Okay, so this is also a natural model to look at from that point of view. Now, this theory has been, studied quite a lot in the late 70s and 80s. In particular, there's a whole series of papers by Jörg Fröhlich, and some joint papers also between Jörg and Tom Spencer. And there's a whole series, there's another series of papers by Galavotti, Galavotti, Nicolo, and co-authors, and Dimmock and Hurd more recently. And there's a very recent work by Falco, who's, I think, was postdoc here, or is still postdoc here? He was postdoc here. And so essentially, so let me just try to very quickly summarize what sort of these results say. They say that in this way of writing things, there are essentially two. Okay, so let me draw a picture. So here there's a value beta square. So beta square is really kind of the inverse temperature of the model. There's a critical value, which is 8 pi. Okay. And if you're above 8 pi, so that's the low temperature regime, so there the intuition from the Coulomb gas is that sort of everything has collapsed into dipoles. Okay. So here there would be a sort of collapse of the gas. And down here, that's the high temperature regime, and so there the intuition is that there's a plasma where the charges are basically free. But then what you see actually, at least in the mathematics, so the partition function here, it becomes infinite at 4 pi. Okay, so below 4 pi, so that's if you want very high temperature, things are very well understood. Okay, so down here it's very well understood. The partition function is finite, so this guy really makes sense as a density with respect to the free field. And you have all sorts of correlation inequalities and so on. You have so you can really make sense of this measure, and it has been done, and you have very good control over it. Okay? And above 8 pi, what one expects is that there's basically there's no way of making sense of this measure at small scales. But what you can do is you can take a discrete version of this and then sort of zoom out and look at how it behaves on large scales. And then what you see is the free field. Okay, so up here, you essentially just see the free field. So somehow the interaction kind of disappears. There's basically no way of building a continuum limit corresponding to this, which still has some interactions built in. And here I think the most complete result in this direction is this recent result by Falco, which shows this very nicely. And in between 4 pi and 8 pi, it's a bit less, so much less is known. So basically the only thing which is known rigorously, as far as I know, is that people have sort of exhibited how the partition function diverges. Okay, so they know that if you take the log of the partition function, then, depending on where you are, so there are sort of intermediate thresholds here. So depending on which interval you're in, there are, this and that many cumulants that you have to subtract, and after subtracting this and that many cumulants, you get something which doesn't diverge anymore in the limit. Okay, so it's that type of very weak result which is known. Okay, but that's pretty much all that's known between 4 pi and 8 pi. And so what we're going to do is we're going to try to build the dynamical object. And there we see that we can actually really go beyond 4 pi. We can't go all the way up to 8 pi. But in principle, the theory that we use in order to build the object works up to 8 pi. Okay, so in terms of sort of the natural boundaries of the theory, the natural boundary is really 8 pi. So in principle, it should be possible to build this object for every value below 8 pi. But then it actually becomes more and more work. Okay, so since for the moment it's sort of preliminary in some sense, so we try to, we did sort of the minimal amount of work required to go beyond 4 pi, and that allows us to go actually up to 16 pi over 3, which is sort of which is bigger than 4 pi. It's less than 6 pi, which is somehow the next transition here. Okay, but so that's sort of that's how far you get by sort of the minimal amount of effort. Then if you make more effort, you can reach 6 pi. If you make even more effort, you should be able to go beyond that. Okay. Right. Now, so the nice thing about our construction is that it gives, it really gives an actual limiting object. Okay, so of course, the way you want to build these objects is always the same, right? So it's as Ivan was saying, that's B-wise discretize. Right? So you take some discrete model, or in our case, it's more B-wise regularize. Okay, so you regularize the thing, so you put some little cutoff parameter epsilon somewhere. Or here you would put a sort of cutoff parameter epsilon in your free field or so. And then you ask yourself, is there a way of building a limit as epsilon goes to 0? And actually what's sort of well known in this business is if you just look at this model written in this way and you just put an epsilon here, then the answer is, well, yes, there's a limit, but it's trivial and it's just a free field, so the thing just disappears. If you want to get a non-trivial limit, you actually have to blow up the intensity of this cosine. So here you actually have to put an inverse power of epsilon in front. And the correct inverse power of epsilon to put in front here is beta square over 4 pi minus beta square over 4 pi. And that's some kind of weak renormalization. It's basically weak renormalization. Okay. But, okay, so the model you really look at is you put an epsilon to the minus beta square over 4 pi. And, okay, so the claim is that this converges to a non-trivial limit as epsilon goes to 0. The limit is not the free field. Okay. Of course, if you put here something smaller, if you put the wrong power, then well, it just converges to the free field. And if you put a too big power, it doesn't converge. And the nice thing about our technique is that it, well, so you can really show that it's not just that things are tight. Okay, you really get a limit. Okay? You really converge to a limit. And you have an intrinsic characterization of the limit, which doesn't refer to the regularization anymore. And here you also see now how, so remember I mentioned that this is a nice toy model because the parameter beta plays a role similar to the role that the dimension tends to play in other field theories. You kind of see that here already, right? In the sense that the power of epsilon that I have to put here depends on beta, okay? Which sort of suggests that the limit of this object is going, the scaling properties of this object in the limit are going to depend on beta, actually. Okay, so, right. Okay, so here's the theorem that we have. So all of this is basically written up, but it's not on the archive yet. Okay, so I can't point you to a preprint. But okay, if somebody's interested, I can always show you the draft. So if beta squared is less than 4 pi, so then again, that's the sort of easy regime. So there we kind of have a very complete result. Okay, so there, if beta squared is less than 4 pi, then there exists a limit. So if you want these processes u epsilon, they converge to some limiting process u in probability. And well, so now I have to say in which space they converge. The limiting process, well, you see, the limiting thing should be something that looks like the free field. The free field in 2 dimensions is not function valued, but it's kind of almost function valued. So this actually converges in probability in, say, continuous function from any fixed interval 0t with values in some spaces of distributions. Okay, and I'm going to call this space C minus kappa of the torus. This is basically distributions of regularity minus kappa. Okay, and this is true for every kappa. So it's sort of things that are almost, they're almost functions, but they're just about not. Okay. So here you can fix any, you can take any fixed time horizon, okay, and you have a limiting process. You have this convergence in probability in this space. This is pretty much the smallest space in which you can expect to have this kind of convergence. And furthermore, the limit here doesn't depend on how you regularize things. Okay. Now, there's a tiny caveat here, which is, you see, so here I wrote psi epsilon. I didn't really say what psi epsilon is, but basically you think of space-time white noise and you hit it with some modifier at scale epsilon. And then, of course, things might depend on the shape of the modifier. Okay. So if you just do that, then yes, things actually do depend on the shape of the modifier in the limit, but they depend on it extremely weakly. And you can completely get rid of this dependency by choosing here a correct constant. Okay, so if you choose this constant here correctly as a function of the shape of the modifier, then you get a limit which doesn't depend on the modifier anymore. Okay, so if you want it, so that's the kind of usual thing that you have in these field theories, is that you end up with a kind of one parameter family of objects, and you always converge towards that one parameter family. But it's not always that easy to guess towards which, individual on that one parameter family you actually converge to. But in this case, you can actually compute explicitly. You can figure out how you have to choose this constant so that you always converge to the same guy. Okay? And so there's really only one guy here. The other thing, actually, here we have it in a way you can make an even stronger statement, which is that you could say, well, one of the physical models that this corresponds to is this sort of equilibrium surface height fluctuation. But in that case, there's really no reason why there should be a sign here. There should really be some periodic function that has the period corresponding to the thickness of a layer of your crystal. So you could take an arbitrary f here, which is just periodic with period 2 pi. So it's kind of like, so it has the same fundamental period as your sine, okay? But then you have harmonics. And you can do that, so we can show that if you take here any finite trigonometric polynomial, actually you get convergence to the same object, okay? So it's not that you get an object that depends on f, it's the same object, provided that it has, that the fundamental mode is not degenerate. Okay, so you can, so that's the other thing which is quite nice with this method, is that it's very robust. Okay, so you can sort of tweak your model around a bit, and you can really control how it converges to the same limit. Okay, but I'm going to.
Let me make sure I understand. Are you saying that the limit doesn't depend upon the periodic function you put there?
Yeah. Well, it only depends on the first Fourier coefficient. Okay. Well, it.
For large beta, I think you're right, but for small beta, I would think there'd be a difference.
There's no you see the reason why there's no difference is because here you fix that, right? So you don't. That beta is fixed.
You're not reordering the perspective.
You're not reordering the different, right? So,
okay.
so that's why. So that's why you'd expect them to disappear.
Okay, yeah.
Right?
If you Wick ordered,
If you Wick ordered each of them, then of course that would be a different story. That's right.
It might disappear, actually. It would disappear if you're in the region between 4 pi and 8 pi, because there would be a higher harmonic
Yeah.
to be pushed into the.
Yeah. That's fine. But here, since you, and so the natural thing, if you think of the model of the interface fluctuations, it's natural that you would have the same, you'd have a fixed prefactor in front, right? You have a fixed shape for that thing, and then there's a fixed prefactor, right? And it just so happens that then it corresponds to Wick ordering for the fundamental.
So you're not adapting in this statement, you're not adapting the prefactor to the function of the periodic function you're using. You're just
That's
using
fine.
the same one for the sine.
Yeah. Exactly. Okay. Of course, formally, it's completely clear that it should disappear, right? Because the higher order harmonics, you have a 2 beta here, but here it's still the same. And
if you Wick order with respect to, you have some periodic function and a Wick order, which is what that is, roughly speaking. Then of course you have different harmonics have different will have different amplitudes, and then you'll have then it's probably true in a region if you're above 4 pi. I would suspect those guys went to 0.
yeah. You're probably right. But below 4 pi you wouldn't, because you would have the second harmonic that falls somewhere within here and contributes. Yeah. And this you could, so here, right, so if you did that, so if we had something that has just the first and the second harmonic, and the first one is below here, the second one is still below the 16 pi over 3, where we can do things, then of course we can still build, right, and then you have a 2-parameter family of objects. Okay. And now between 4 pi and 16 pi over 3, we have essentially the same result, but it's only local, okay, local in time, right? In the sense that, there's the problem of obtaining a priori bounds, and there are no good a priori bounds above 4 pi, and somehow the question of building a local well-posedness theory is always disjoint somehow from the question of building a global one where you have to use some kind of a priori bounds. And here we don't have a priori bounds, so we have a local well-posedness theory. Okay. Presumably it's global, okay, but we don't have a proof that it's global. You have to have, but you have, so if you wanted to, you would have to have sort of good tightness, right? So you wouldn't have to have sort of, really converges to an invariant measure or anything like that, but you would need to have some tightness of, you would need some kind of tightness of these measures in a small enough space, in some space like this with a kappa that's not too big. So if you had that, then immediately the local would become global. But that's a separate problem. Okay. So let me okay, so let me show you how you prove this. So the first thing we do is we actually massage the equation a little bit to rewrite it in a form which is kind of nicer for us. And so that's why I introduced the phi. So we just introduce the free field. Okay. And let me just remove epsilons, but with the understanding that there are epsilons everywhere. And then the whole point is to get things uniform in epsilon. And once you have things uniform in epsilon, you use there's a simple calculation that shows you actually have convergence and not just boundedness. Okay, so you have the free guy, and you rewrite u as a perturbation of the free one. Okay, so you write it as the free one plus something else. And then you see what you get. So you get that dtv is equal to 1/2 Laplacian v. And then you get this, well, there's still this e to the epsilon to the minus beta square over 4 pi. And then you have a sign of, well, u plus v plus phi. And then you just use trigonometric identities. Okay, so you get something like a sine of beta v times cosine of beta phi plus, the same term with cosine and sine reversed. And now you put these two guys together, okay? And you call this guy psi, okay? So you call psi epsilon, well, or rather, I define psi epsilon to be epsilon to the minus beta square over 4 pi times e to the I beta phi epsilon. Okay, and then that's just the real part of psi. Yeah? So now the problem becomes something like dtv is equal to 1/2 Laplacian v plus sine beta v times, well, let me write psi epsilon c, so that's the cosine part of that one. So it's the real part of this guy. And then there's another term with a cosine at the imaginary part of that guy. Okay? And now you see there's no inverse powers of epsilon in front anymore. Okay, so they are completely absorbed into that guy. So now, okay, so here you have, in a way, you have just a PDE with some kind of random coefficient. Now, if this random coefficient converges to a limit in a nice enough space, then you can just apply standard PDE techniques and you get a solution theory. Okay? And that's exactly what happens below 4 pi. Okay? So 4 pi turns out to be exactly the limit where below 4 pi you have a nice, basically classical PDE theory for this equation. Okay? And 4 pi is exactly the threshold where the classical PDE theory breaks down. And we see how that happens. But let's first see why. So why is 4 pi a natural threshold here? Well, the question is in which space, how singular does that guy become as a distribution as epsilon goes to 0? Okay? Now suppose that you have convergence of this guy to some limit in some space of distribution of order minus eta. And what I mean by this, so now let me be a little bit more precise on what I mean by these sort of Hölder spaces with negative exponents. So what I mean here is really that, so a distribution psi belongs to this space, if when I test it against the localized test function, okay, so this is a test function that sort of looks like this and is localized on scale lambda. And I really take here, spaces of distributions on space-time. And so this is a space-time test function. And scale lambda is really lambda in space. And you should take lambda square in time because of parabolic scaling also. Okay, so that if you take this, then this is bounded by lambda to the minus eta. Okay, so that's my definition, if you want, of these spaces. And so suppose that you have convergence in a space like this. Okay? That means that that guy belongs to this minus eta space here. Now, by Schauder, you would expect, therefore, V to belong to C2 minus eta. Okay, you gain two derivatives from the heat equation. So if that guy is in minus eta, that guy should be in 2 minus eta. That means that here you have to multiply a distribution of regularity minus eta with a function of regularity 2 minus eta. So say eta is less than 2. Okay? So if you're below minus 2, then this guy is not even a function. Okay? But if, say, you're above minus 2, then you have a product here between a function and a distribution. And it's basically well known that you can do that if and only if this guy is bigger than that guy in absolute value. Okay, so there's a natural condition here. There's a natural condition, which would be that 2 minus eta should be bigger than eta, and which really means that eta should be less than 1. Okay, so if this guy is less singular than something of order minus 1, then you have perfectly nice PDE theory. Okay, you can just get away with Schauder estimates and very weak kind of arguments. Okay. Now, let's see. So let's try to see what is the regularity of this guy. Okay, so what happens if I test this guy against one of these test functions? Okay, so I compute the expectation of psi epsilon tested against the test function square. Okay. So that's just a double integral of expectation of, now this guy was e to the I beta phi, and here you would have a phi epsilon of, say, x minus phi epsilon of y times phi lambda of x, phi lambda of y, dx dy. Right? You have this, well, and there's the epsilon to the minus blah, blah. Okay? Now, and here x and y are really space-time variables, okay? But I still just call it x. I don't want to have t's all over the place. Okay? So this is really a space-time variable. So there are things in R3 and not in R2. Okay. Now, this is just a Gaussian thing. Okay, so I can compute this expectation. It's trivial. So here I'm going to use the fact that if you have Gaussian random variables xi, and you compute the expectation of e to the I, well, remove the beta because you can always absorb it into the xi's, sum of xj, okay? Then if these guys have covariance matrix Cij, then this is just e to the minus sum over all I and j's of Cij. Okay, so that's a very simple calculation. And however, what we have here is we have this factor epsilon to the minus something in front. And it turns out that factor, the way we choose it, what we actually put out in front here is e to the plus sum of Cii. Okay, so if you want that factor, this epsilon to the minus beta square over 4 pi, the reason why it shows up is that this is actually really just e to the covariance of the epsilon regularized field evaluated at the origin. Okay, or evaluated at any point. And so now if you multiply by this, well, then it kills the diagonal terms. That's the ones that tend to lead to singularity, so you only keep the off-diagonal terms. And so I can also put a 2 here and keep to I less than j, for example. Okay. So if you plug this in, well, you get just this double integral. And so now I have a e. And there's a half. There's a half that I forgot, which cancels out the 2. Okay. So here you end up with an e. There's still a beta square. And then what you have is you have just the covariance function between, so let me write C epsilon for the covariance of that field. And so you just have a C epsilon of x minus y times phi lambda of x, phi lambda of y, dx dy. Now, let me see if I didn't mess up a factor 2 because, no, I didn't mess up a factor 2. Okay. Now, it turns out that computing the covariance of this guy, you can just do it. It's a simple calculation. For the static one, it would just be the covariance of the free field. That would just be a log. But you have to figure out the prefactor because you have an exponential of a log then. Okay, so you better know what's the factor in front. It's 1 over 2 pi. Okay, so that's where these 2 pi's come from. So it turns out that the covariance function of this free field, C epsilon of x, essentially it behaves like 1 over 2 pi log of norm of x. And because of the regularization, there's an epsilon here, and there's a minus to make it positive at small scales. And then there's an order 1. Okay? So this is true uniformly in epsilon. And this is true as space-time variables. So x is a space-time variable, and this is the parabolic norm. Okay, so it's really x plus square root of t. Okay, but then this is really true. And this order 1 bit sort of depends on where you are on the parabolic unit circle somehow. And so now you can plug this in here. And so you see that this is something like a double integral of, and so now here you have a log of x minus 1 over 2 pi, a beta square over 2 pi log of x minus y. So you basically have an x minus y to the minus beta square over 2 pi, phi lambda of x, phi lambda of y. Okay? And now you see why 4 pi and 8 pi are thresholds. Okay? So first, why is 8 pi a threshold? So 8 pi is when this is a minus 4. And parabolic space-time has scaling dimension 4. Okay? Because you have 2 space dimensions, and there's time, but time counts double because of parabolic scaling. Okay? And so when beta square hits 8 pi, this is no longer integrable. Okay. So when beta square hits 8 pi, actually the scaling, so when beta square is bigger than 8 pi, then if you want to get a limit here, the scaling here changes, and the limit is just a white noise, because you just, you have here something with a non-integrable singularity, and then the only way of rescaling it is to make sure that it integrates to 1, and then it becomes a delta function in the limit. Okay? And so you just have convergence to a white noise. And that's, but if beta square is less than 8 pi, okay, then you have something integrable here. And so you can expect, at least you can hope, that you have convergence to something non-trivial. Okay? And now, why is 4 pi special? Well, if you compute this, you just use the scaling properties of these functions, and you figure out that you get lambda to the minus, let's think you should get exactly beta square over 2 pi. Okay, so this, yes. Lambda is fixed, uniform in epsilon. And of course there's, right, yeah, so of course you can be a little bit more refined and figure out how it depends on epsilon as well. It's not difficult. Okay, but you have a bound like this, which is uniform in epsilon. That's what you get uniformly in epsilon. And so now you see, so this is this quantity squared. So that tells you that this guy should be of order lambda to the minus beta square over 4 pi. Right? So you would expect, if you have a convergence, you expect that, so the best you can hope for is that this convergence takes place in a space with eta bigger than beta square over 4 pi. And so now you see that threshold eta equal 1 exactly corresponds to beta square equal 4 pi. Okay? So you see that if beta square is less than 4 pi, then you can expect, at least from this just second moment calculation, you could expect to have convergence in a space C minus eta for eta less than 1, and then you can just apply usual normal PDE techniques. Okay? Whereas if beta square is bigger than 4 pi, that's just not true. Okay? And then that means that this equation is just ill-posed in general. Okay? And so the problem is to make sure, to somehow study the ill-posedness of that equation if you want to go beyond 4 pi. Okay, but here, so first the proposition is that it's true. So proposition, these psi epsilons converge to a limit psi in probability in C minus eta for every eta bigger than beta square over 4 pi. So this is a theorem. Now, what I showed you was a motivation. It's not a proof. And the reason is that, if these guys were Gaussian, then it would be a proof, essentially. Because if they were Gaussian, then if you have a bound on the second moment, you have equivalence of moments. So you have the same bound on sort of the corresponding bound on every higher moment. And then there's a Kolmogorov type criteria that gives you this. Okay? But in general, of course, just because you have a second moment bound doesn't give you a fourth moment bound. And these things certainly do not at all have equivalence of moments. Okay? They don't behave at all like Gaussian objects. And so if you want to prove this, well, the only way we figured out, which is sort of the brutal thing, is to get a bound like this, but for every moment here. And you can imagine that it sort of gets trickier for the higher order moments. Okay, but you can do it. So you can control all moments of these guys, so you can control convergence of all moments. And there it's actually good enough to apply some kind of Kolmogorov type theorem. And that gives you convergence in these spaces. And if I have time, I might show you how to. It's actually, so there's a neat, when you want to bound these objects, the higher order moments, there's actually kind of a neat physical picture that shows up in a way that you have to somehow, in a way, you have to use some sort of screening of the charges. So you have to use the fact that things tend to pair up into dipoles, and then the dipoles appear to be neutral for the other charges. So there's a kind of picture like that that emerges when you try to bound these higher order moments. So it's kind of neat. So if I have time, I might show you. Okay. Anyway, so if beta square is, so if you're above 4 pi, then, well, this is still true. So this is true for every beta square up to 8 pi. Okay? So this is true for beta square in 0, 8 pi. But above 4 pi, it's just kind of useless in order to give you a well-posedness theory here. Okay? And as a matter of fact, so there's, in some sense, it's a miracle that these guys still converge to a limit. Okay, so why is it a miracle? Because if you looked at the following equation, so look at dtv equal to 1/2 Laplacian v plus just v times this psi epsilon c. Okay? Now that should be much easier to deal with than this equation. Okay? So now if beta, so here, if beta square is bigger than 4 pi, this one does not converge to a limit. Okay? So if beta square bigger than or equal to 4 pi, here you have no convergence. Okay, so it shows you the fact that, but I was claiming that these guys do converge. Okay, all the way up to 16 pi over 3. So there's magic cancellation that goes on because of the, essentially there's a cancellation between some divergent term arising from this interaction and another divergent term arising from the other interaction, and they exactly cancel out. Okay. And if you just write an arbitrary equation like this magic cancellation doesn't happen. Okay. So on the other hand, the general theorem that you have is if you take here an arbitrary nonlinear function, say I call it fc, c goes with, and fs of v psi epsilon s, okay, and you correct for the divergences. So the way you have to correct is like this. So you have to subtract the correct constant times epsilon to the 2 minus beta square over 2 pi times fc derivative of fc plus fs times derivative of fs evaluated at v. So if you take this equation, now this, you see this factor here diverges when beta square is equal to 4 pi. Oh, well, if beta square is equal to 4 pi, it's a log. Okay, and if beta square is bigger than 4 pi, it diverges like some inverse power of epsilon. And so the theorem here is that if you look at an equation of this type, this converges to a limit all the way up to this 16 pi over 3. And actually, we think it's true up to 6 pi even. Okay, so here you have convergence to a limit for beta square less than 16 pi over 3. And we really think it's actually 6 pi. Okay? And now you see, in the case of the model we're looking at, one of these is a cosine, one of them is a sine, and so you get sine times cosine minus cosine times sine, and so it cancels out. Okay, and so this term, so you don't see this term. It just disappears, and that's why the original equation actually converges to a limit. Oh, but if you have a general periodic function, the higher order harmonics, at this stage, they already get multiplied. They get multiplied with a guy like this, but with the wrong normalization, and so that guy actually goes to 0. But then you still have to, when you're actually above 4 pi, it goes to 0, but it doesn't go to 0 in a quite good enough space. But then you have to control the interaction between these guys, and it turns out that they actually go to 0, and so it still works out fine. Yeah. Okay. Now, so let me erase, let me erase this. So how do you prove that type of result? So actually, there's a kind of general theory. Okay, so there's a general theory I've been sort of developing over the last couple of years, which gives you a machine, essentially, that allows to prove convergence of solutions to equations of that type driven by some very singular objects that don't need to be Gaussian. So this was a nice toy model because you had a driving noise, which is not Gaussian. And so, to see if the whole machinery still applies. And what it says is that if you look at the solution map to an equation of this type, you can basically factor it into 2. So you have so here you have this the single object that drives it. So there would be, if you want, the psi c epsilon and the psi s epsilon. And here you have your solution, so that's your v. Okay. And what you do is you actually build some intermediate object, which I'm not going to go into detail on, in such a way that the solution map actually factors to 2. And the problem is that, so as a function of this guy, the solution map is not continuous. Right? I mean, you see it here. It's like if you take this equation here and you didn't put these correction terms, well, obviously the solution is not going to be continuous in these spaces as soon as eta is bigger than 1, because we know that it doesn't converge to any limit, since you have to put a sort of infinite correction in order to get a limit. Okay? So the solution map is not continuous, but it factors into something discontinuous, which is easy to understand, and something continuous, which is more difficult to build, but you build it once and for all. Okay? So you factor it into 2-bit, where this is nice and continuous, and this is discontinuous, but explicit. Okay, so it's explicit in the sense that there are sort of finitely many objects of which you need to show by hand that they converge to limits. And if you can show that they converge to limits, well, then the solutions automatically converge to limits because these things are composed with something which is continuous. Okay? So what you gain here is the explicit bit. And explicit really means that these are multilinear objects of these guys. Okay? So they are very explicit. And now what happens here is that the way these kind of infinite in the limit correction terms show up is that there's actually some kind of there's a group of transformation that acts on these objects up here, where typically what happens is if you take these regularized objects and you move them into this space, then they actually don't converge to a limit. But then you can act on them with an element of this group of transformations, and you can make them converge. And the effect of this group of transformation is to somehow change the equation and to make these terms appear. Okay? So these terms appear, if you want, automatically as a consequence of the action of this group of transformations there. Okay? But so, okay. So I'm kind of running out of time. So let me show you. Yes.
So the last time I can see the circular expectation was the product of the
So this is, well, it's not an expectation, right? But it's, of course, okay, so for the stochastic analysts in the audience, this last term actually looks very much like an Ito-Stratonovich correction, okay? And that's not a coincidence at all. Okay, so it really is, the way it shows up is exactly like the Ito-Stratonovich correction. And it's just that the case of usual SDEs would somehow correspond to eta equal 1, where this thing doesn't diverge. Well, here it still diverges logarithmically, but in the case of usual SDEs, because of time reversal symmetry, it doesn't diverge. But here it diverges. But it's more, sorry? It's bilinear in F, yes. And then you would have, when you cross these thresholds, if you wanted to build sort of, you have to build higher and higher order objects here, and they in principle give rise to more and more correction terms that are bilinear, trilinear, quadrilinear, etc. And of course the expectation is here is that they would all drop because of the symmetries of the equation. Okay, so you would always have a cancellation of these terms and they should always disappear. Now, yes, so maybe I'll show you just what is the object that you need to control here. So it's very simple. It turns out that what you need to control is basically the Green's function, so the heat kernel, convolved with this psi epsilon multiplied by psi epsilon. Actually, the thing which is more difficult to control is when one of them has a complex conjugate. So if you look at this term here, you can do a similar kind of calculation, and you can figure out that the expectation of this diverges when beta square hits 4 pi. Okay? And so now the surprising thing is that the way you renormalize it is you do as if this was a Wick product. And of course, in principle, this is nonsense because these guys are not Gaussian. Okay? And so there's no reason why turning the product into a Wick product should actually work. But it works. Okay? So what you do is you just subtract here a large constant, and this large constant is exactly this constant here, okay, which is the expectation of this term. Okay, so you subtract the expectation of this term, and then you have to show that these guys are actually some kind of suitably recentered version of them. But essentially, you have to show that these guys converge to limits. Okay? And now now it's again the same problem as before, so it's relatively easy to show that the second moment of these guys behaves in the right way and that they converge to a limit. But then they're not Gaussian, or they're not infinite Wiener chaoses. Okay, so you have, again, no equivalence of moments, so you have to show that all the higher moments are controlled uniformly with the correct powers of lambda. Okay, and so just having some control which is uniform in epsilon is not too difficult. The difficult thing is to have exactly the right behavior in lambda, because there are very subtle cancellations, actually, that you have to extract from this. Okay, but I think I'm running out of time, so I think I'm going to stop here. So it would be nice. The problem with this model is that it's enormous amount of work to actually control this object. Okay, so everything is very explicit. Okay? So if you can control these objects, you immediately get these nice convergence results. You get the fact that the limit doesn't depend on how you regularize things and so on. But even this second order object is already very difficult to control. And so it would be really nice if somebody came up with a nice systematic way of understanding these objects or controlling these objects. Or somehow, if you knew that you had equivalence of moments here, that would help a lot. And there doesn't seem to be any general theory that tells you something like this for these type of objects. But yeah, okay, so I think I'll stop here. Thank you very much for your attention.